Imagine a place where atoms grind to a halt, where time itself seems to slow down, and heat simply ceases to exist. We're about to embark on a journey to explore the extreme limits of cold, venturing into realms that defy our everyday experiences. Prepare to be surprised. The coldest place in the universe isn't necessarily what you think. It's not lurking in the vast emptiness of space, but rather, it's been created much closer to home. Let's start with the basics. Cold isn't something that exists on its own. It's simply the absence of heat. Temperature is a measure of the average speed of atoms and molecules. The faster they move, the hotter something is. Slower motion. That equates to colder temperatures. Now, imagine slowing those atoms down, until they're practically motionless. This brings us to the concept of absolute zero. That's 0 Kelvin, or minus 273.15 degrees Celsius. At absolute zero, atomic motion theoretically stops. It's the point where all the jiggliness of matter hits rock bottom. Absolute zero represents the theoretical bottom of the temperature scale. But here's a question that has puzzled scientists for years. Can we ever actually reach absolute zero? When we think of cold, deep space often comes to mind. It's a vast, empty expanse, seemingly devoid of warmth. The average temperature of the universe is around 2.7 Kelvin. This background hum of cold is due to the cosmic microwave background radiation, the afterglow of the Big Bang. But even within this frigid cosmic ocean, colder regions exist. One of the most notable is the Boomerang Nebula. The Boomerang Nebula is the coldest naturally occurring place we know of. Its temperature dips to around 1 Kelvin, which is incredibly close to absolute zero. What makes it so cold? It's expanding rapidly, causing the gas within to cool down even further than the surrounding background radiation. Space is cold, yes, but it turns out it's not the coldest place. Here's where things get really interesting. Humans have actually managed to create temperatures colder than anything found naturally in outer space. In particle physics labs around the world, scientists are pushing the boundaries of cold, achieving temperatures mere fractions of a degree above absolute zero. They use sophisticated techniques like laser cooling and magnetic trapping to slow down atoms to a near standstill. In 2017, researchers at MIT achieved a mind-boggling 500 picokelvin. That's 0.0000000005 Kelvin. NASA's Cold Atom Lab on the International Space Station has achieved similar extreme lows. Why go to such extremes? These ultra-low temperatures allow scientists to study quantum behavior in ways never before possible. For example, they can create Bose-Einstein condensates, where matter behaves as a single giant superatom. So if we can get so close, why can't we just reach absolute zero? It turns out there's a fundamental reason why it's impossible. The answer lies in the third law of thermodynamics. This law states that as a system approaches absolute zero, the process becomes increasingly difficult. In essence, it would require an infinite amount of energy to remove the very last bits of heat from a system. Furthermore, even in the emptiness of space, quantum fluctuations prevent perfect stillness. There's always a tiny bit of energy present. Absolute zero is a cosmic limit, a fundamental property baked into the very fabric of the universe. So how cold can it get? Colder than the depths of space, colder than your freezer, colder than the Boomerang Nebula. We can create conditions that are almost unimaginably cold, but we can never quite reach absolute zero. It remains an elusive theoretical limit, a testament to the strange and wonderful laws that govern our universe.